thermodynamics. So let us discuss few multiple choice questions. The first question is, when an ideal diatomic gas is heated at constant pressure, when it is heated at a constant pressure, the fraction of the heat energy supplied which increases the internal energy of the gas is. See here, they have given an ideal diatomic gas which is heated at a constant pressure, The fraction of the heat energy supplied which increases the internal energy of the gas is. See here, we have the equation, that is delta U is divided by delta Q is equal to CV into delta T divided by Cp into delta T. So which can also be written as R divided by gamma minus 1, this whole divided by R gamma divided by gamma minus 1. So if we simplify this equation, R gamma minus 1 will get cancelled. Therefore, we will get it as what? 1 divided by gamma. That is nothing but 1 divided by gamma value is, they have given it as for a diatomic gas. For a diatomic gas, it is 7 by 5. Therefore, it can be written as what? Sorry, 5 divided by 7. It can be written as 5 divided by 7. That is option D is the right option here. So when an ideal diatomic gas is heated at constant pressure, the fraction of the heat energy supplied increases the internal energy of the gas, and the value is 5 divided by 7. Delta U value they have asked. Next question. The work of 146 kilojoule is performed in order to compress 1 kilomole of gas adiabatically. And in this process, the temperature of the gas increases by 7 degrees Celsius. The gas is, see here, the work is given as 146 kilojoule is performed in order to compress 1 kilomole of gas adiabatically, and in this process the temperature of the gas increases by 7 degrees Celsius. So the molecule, whether it is monoatomic, diatomic, triatomic, or a mixture of mono and diatomic, let us see here. According to our first law of thermodynamics, we can write it as delta Q is equal to delta U plus delta W. Okay. So as it is specified, it is an adiabatic process. This equation will be delta Q will be 0 is equal to delta U plus delta W. Therefore, we can write it as delta U is equal to minus delta W. So what is the value of delta U? Delta U can be written as mu CV into delta T. Mu CV into delta T, which is equal to minus delta W. So I'll simplify this equation for CV is equal to, I'll get it as minus delta W divided by mu into delta T. Now, so we can substitute the values now. That is, CV is equal to minus into bracket. So as we are doing the work on the system, it will be minus 146 into kilo it is. Therefore, 10 raised to 3. This entire divided by mole. So 1 kilomole they have given. That is 1 into 10 raised to 3 into delta T. That temperature is 7. Temperature is 7 here. So if we simplify this, we will get it as CV is equal to 20.8 joule per mole per Kelvin. Joule per mole per Kelvin here. This is the value of what? CV. Okay. So when we will get the value of CV, we can calculate so this is the value of CV now. So just we will verify the equation. See, if I take the equation, CV is equal to 5 by 2 into R. This is what? 5 by 2, it is for diatomic molecule into R. So 5 by 2 into R value is how much? It is 8.3. So if I do 5 by 2 into 8.3, how much I'll get? I'll get it as 20.8 joules per mole per Kelvin. Okay, which means that it is a diatomic molecule. It is a diatomic, means how much value CV you have calculated, that is same for your that is CV for diatomic molecule. Therefore, when they are satisfying, we can say that the molecule is a diatomic. Suppose if you are not getting it for diatomic, CV is equal to, we can take the expression for monoatomic, then we can calculate it. If it is matching with that, then we can say it is as a monoatomic. So the degree of freedom for di, mono, triatomic and polyatomic, knowing the value is very, very important. Okay. So we can say that the molecule is diatomic in this case. Next question. A thermodynamic system is taken through the cycle PQRSP. It is taken through PQRSP process. The net work done by the system is, so we need to calculate the net work done here, that is given by, so work done is equal to area under rectangle PQRS, area under rectangle PQRS. So area of rectangle is given by length into breadth, that is PQ into SP, that is equal to 300 minus 100. You can see in the figure, that is PQ value I have written, into 10 raised to minus 6 as it is given in CC, into SP value. SP is, it is 200 minus 100 into 10 raised to 3, into 10 raised to 3, which is equal to 20 joules, which is equal to 20 joules. That is what the work done here. Okay. So direction of the process is anti-clockwise. If you see the process here, the arrow mark you can observe in the given figure, it is anti-clockwise. Therefore, what we can say, when it is in the anti-clockwise direction, we can take the value as minus 20 joules. If it is in the clockwise direction, the option would be A. But as it is given in the anti-clockwise direction, the option B is the correct option, as we will get it as minus 20 joules. Next, an ideal gas is taken around ABCL as shown in the figure. The work done during a cycle is, so we need to calculate the work done during the process. If you see the figure, in the previous figure it was rectangle, now we have triangle. We can apply law, that is area of triangle formula. That is, work done is equal to area of triangle ABC, which is equal to 1 by 2 AC into BC. That is nothing but 1 by 2. So according to the figure, just label this. AC is 3V minus V into BC is 3P minus P, which is equal to, it is 2PV. It is 2PV. That is, option A is the right option here. Next question. How much energy is absorbed by 10 kilomole of an ideal gas if it expands from an initial pressure of 8 atmosphere to 4 atmosphere at a constant temperature of 27 degree Celsius? See what they have asked. How much energy is absorbed by 10 kilomole of an ideal gas? So number of moles, pressure difference and temperature are the given quantities. As the temperature is mentioned as constant, we can write it as it is the isothermal process. Therefore, work done is equal to mu R into T log to the base E inside the bracket. It is P1 divided by P2 or initial divided by final. Substitute the value. Mu value is given as 10 kilo. Therefore, I'll write it as 10 into 10 raised to 3 into R value is 8.3 into T value is 27 degrees Celsius. In terms of Kelvin, it will be 300. Then log to the base E into bracket 8 divided by 4. So do the simplification here. If we do the simplification, we will get it as 1680 into 10 raised to 4 joules. 1680 into 10 raised to 4 joules. Or it can also be written as 1.680 into 10 raised to 7 joules. So we can see the options here, that is, which is near value, whichever the near value is there, that we can take here. Option C we can consider, which is 1.65. Here it is 1.68. Right? Then next question. An ideal gas at 27 degrees Celsius is compressed adiabatically to 8 by 27 of its original volume. If gamma is equal to 5 by 3, then the rise in temperature is, here we need to calculate the rise in temperature. The process is adiabatic process. So take the equation of adiabatic process, that is given by T2 divided by T1 is equal to V1 divided by V2 whole to the power of gamma minus 1. So we need to simplify it for T2 is equal to, that is T2 is equal to T1 into bracket V1 divided by V2 raised to gamma minus 1. That implies T2 is equal to T1 into bracket V1 divided by 8 divided by 27, that is the value of volume, into it is V1, okay, that is nothing but 300 into 27 divided by 8 raised to 5 by 3 minus 1. So simplify this. 5 by 3 minus 1 is nothing but 2 by 3. 300 into bracket 27 by 8 to the power of 2 by 3. So simplify this, we will get it as 675 Kelvin. We want answer in terms of Celsius. So 675 minus 300 is 375 Kelvin. That is option B is the correct option here. Option B is the correct option. So we have completed thermodynamic synopsis and few numericals. In the next class, let us discuss with you few more questions. Okay, students, thank you.